So let's now introduce a model one, the empty model. So remember the intersectional MAIHDA approach has two classic multi-level models which are going to be fit to do the analysis. So we've done quite a lot of descriptive analysis already, but we're now going to do this in a model framework and get extra insight. So this first model, model one, the empty model, it's really going to measure the extent to which this individual outcome heterogeneity in BMI, to what extent can we explain it by sociodemographic characteristics? And by this, I mean as richly as possible. So by the intersections, by the 382 intersections. And really, this is going to be equivalent to saying to what extent can main effects and all possible interactions between them for these five characteristics. Remember, they are sex, race, education, income, and age. Collectively, what is the explanatory power versus other factors not in the model? Okay, so that's going to be very useful because that tells us about the discriminatory accuracy of the model, which we know is going to be low, but we want to quantify it. But also, we're going to address those very noisy observed stratum mean by optimally predicting the mean outcome for each stratum, where we're going to use the information on each stratum, but borrow strength from the distribution at large to get almost smoother predictions, less noisy. So let's do it. So let's plunge into some model equations. I'll walk you through it carefully because I understand not everyone likes equations. So the model starts off like this. We have a dependent variable, outcome, BMI sub ij. So the subscript ij is the body mass index score for individual I in stratum J. And this is going to equal beta 0j. You can think of this as the true stratum mean, okay? The mean BMI score for people in stratum J in the population at large, okay? That's the thing that we want to make an inference about from the sample data. And of course, within that stratum, and in every stratum, there's a lot of diversity in BMI scores, and this is picked up by the EIJ residuals, how people deviate from their mean. So let's look at the beta 0j in a bit more detail. The beta 0j, the way it's parameterized is, remember, this is the mean BMI in stratum J in the population at large. This is going to equal beta 0, which is a mean across all the stratum. So it's the mean of the stratum means. And so the UJs are going to quantify how each stratum deviates from the average stratum. Okay. Substituting the second equation into the first gives the third equation on the slide. And so here we have the body mass index score for individual I in stratum J is equal to the overall average BMI score across all the strata, plus how the strata that they actually belong to, J, how much higher is the mean BMI for that stratum, UJ, and then for that particular individual I within that stratum, how much higher or lower if it's a negative value is their observed BMI, EIJ. So this is really a classic two-level, multi-level linear regression model. We've got a continuous outcome, BMI. We've got an intercept, beta 0. We have no explanatory variables at the moment. Okay, the beta 1 times x1 plus beta 2 times x2 comes later in model 2. But we do have this decomposition of the total residual into a stratum-specific random effect and an individual-specific residual. And so those are not parameters, those are residuals, they're latent variables. And so just like in linear regression, we need to specify some distributional assumptions to complete the model. And here are those assumptions. So in linear regression, you'd often think of the residuals, oh, they're normally distributed with mean 0 and a constant variance, homoscedasticity. Well, we have the same thing here, but we have two sets of distributional assumptions. We have one set at level 2 for the stratum random effects, assume normally distributed with mean 0 because they're deviations from the average stratum, and sigma u squared governs the variance of those UJs. And that sigma u squared is referred to as the between stratum variance. That is quantifying how variable our stratum means, which is the very thing of interest. The greater the variability, the greater socio-demographic inequalities. But we have to consider that in light of the underlying individual heterogeneity that is seen within any given stratum. Okay, these residuals of how my observed BMI deviates from what we expect for the stratum to which I belong, those are modeled as normally distributed zero mean, because they're deviations, sigma e squared, which is the within stratum variance, a parameter to be estimated which quantifies the degree of individual heterogeneity that we have within a typical stratum, which we know is substantial. Okay, so we've done some algebra, so let's get into some results. So we're going to fit this model by maximum likelihood estimation. So if you're a Stata user, you'd use the mixed command, or maybe even xtreg, mle. If you are an R user, you'd use the LME4 package with the LMER function within that. So nothing complicated, and that's the nice thing here. We're using what are now kind of well-established methods available in all standard software, but we're using multi-level modeling in this kind of innovative way and tying it to intersectionality as well. So this model one, what we can see here is we have a table of results. We have the different parameters, beta 0, the intercept giving you the overall average BMI. We have sigma u squared and sigma e squared. Those were the between and within stratum variance. And this is decomposing the individual heterogeneity into how much of it is between the means and how much of it is between the individuals in each stratum. So you have point estimates and standard errors here as well. So the overall average BMI, the mean across all stratum means, if you like, is 28.1. Between stratum variance, which is quantifying how much do those 382 strata vary in their means, just 1.8. Whereas within the average stratum, we're seeing a variance in individual BMI scores of 34.5. So really, we don't have much going on between the strata. And actually, it's 5%. So 0.05 is saying that 5% of this total variability is at level 2, with 95% being at level 1. Okay, so only 5% of the variation in individual BMI is between stratum means. Okay, and the deviance here is -2 times the log likelihood, used for likelihood ratio tests, but we're not doing that here, so I won't say more about that. On this slide, we are formalizing the VPC. I've already done this calculation. So really, we're just dividing the between stratum variance, the point estimate of 1.8, divided by the summation of the between and within, which is 1.8 plus 34.5. You do the maths, comes out as 0.05. So the proportion is 0.05 of the variation in the outcome individual BMI. So that's often multiplied by 100 to express as percentages. And so you can say 5% of the variation in individual BMIs between the stratum means, 95% within. And this links into the topic of discriminatory accuracy. And this is an important feature of the approach. So MAIHDA is multi-level analysis of individual heterogeneity and discriminatory accuracy. And so by that, in this context, we mean how valuable is knowing stratum membership? If I know which stratum that you belong to, how predictive is that of your individual BMI? And the answer is not very, okay, because it's only explaining stratum membership 5% of what's going on. And so this is just keeping our interpretation of stratum means in check, stopping us from over-analyzing differences when we come on to it. So we'll repeat this point later. I wanted to kind of visualize the variance partition coefficient. I wanted to kind of visualize just how small it was. So what I've done here is, off the back of the model, I've drawn two implied distributions of BMI for two different hypothetical strata. One with a rather low mean BMI, okay, which is going to be this here, and the light grey area. So this is like a smoothed histogram, because we've got lots of people in this hypothetical stratum, and they've got a low mean, and this is really low. This is like at the 2.5th percentile of the distribution. And let's go wild and choose another color. Why not pink? Here is another distribution which has a high mean at the 97.5th percentile of the distribution. And here I'm drawing the smoothed histogram, or just highlighting it rather badly. I'm not very good at using these crayons. Crayon's a bit sticky. Here we go, doing my best. Okay, so when you've got a VPC and only 5% of the variation is between the stratum means, like this, you can think of this kind of, let's go crazy with the crayons. This kind of variation here, well, that doesn't work very well, but it's variation in stratum means, but actually within any given stratum, I've got this much greater variation around the mean for the first one, and this variation around the mean for the second. So these two distributions are overlapping, and that darker shade triangle in the middle of the plot is the overlap. So what this is basically saying is that within any given stratum, we see practically all of humanity. We see the very lowest BMI scores and the very highest BMI scores. Yes, the pink distribution is to the right of the yellow distribution, but really there's so much overlap still. So there's plenty of people with low BMI in the pink distribution, and there's plenty of people with high BMI in the yellow distribution. So this is, again, what we mean by lack of discriminatory accuracy. Just knowing whether you're in the yellow or the pink distribution is going to tell me very little about your actual individual BMI score. That's a visualization of the fact that this is low VPC. If it was a high VPC, these distributions would pull apart and there'd be very little overlap. Okay, so let's have a slightly technical slide here. Just getting my my pencil out again, and get my highlighter going. So one thing that we've seen in these model results is that the estimated mean is 28.1, but this is bigger than the sample mean of 27.9 that we saw earlier. Now the discrepancy is tiny, 0.2 of a BMI point. But it turns out that in many intersectional MAIHDA applications, you can see quite a pronounced difference between these two numbers. And we're referring to both of them as the mean, so it seems odd that they differ in their number. And the reason why we see kind of differences quite often in intersectional MAIHDA applications is because we have quite unbalanced data. And so by unbalanced, remember the stratum size varies a lot. We've got some really tiny ones, some big ones. If you have individuals within geographic administrative areas, those boundaries are often drawn in such a way to have a similar number of households in each geographic area. And so you'd end up having a rather more uniform distribution here. And with balance, you get less discrepancy. Okay. And the reason for this is that I've gone too far. Okay. Getting carried away. Is that whereas the sample mean is a straight average of the 33,000 data points, which is equivalent to a frequency weighted average of the observed stratum means, the estimated mean, that is the parameter estimate we get back, is neither of those things. Okay, it's not a frequency weighted average. It's not a straight unweighted average of the observed stratum means. It's called a precision weighted average. And the idea here is if we go back to this kind of table, this league table, and remember we saw, all these different observed strata, one row per strata, they've all got different means. So what's the global mean? Do we take a straight average of all these numbers? Well, no, that wouldn't make any sense because some have a tiny sample size, where some have a big, and where it's a big sample size, it's much more trustworthy than small. Okay, so we could do a frequency weighted average where we give a kind of a weight of 149 versus a weight of 3 essentially for these things, but we don't do that either. That's too extreme. we do something in between, which is called a precision weighted average. Okay, and this is standard multi-level modeling, but we don't often talk about it. And it turns out the precision weighted average is the optimal because it respects the or learns from the degree of clustering in the data. So it's better than just a frequency weighted average. So if we get back to that slide here, we can see the algebra here. We've got our precision weighted average here. Okay, so we are averaging the observed stratum mean, but we're weighting them by Wj. And Wj is the weight, and it's called the precision. And the precision of an estimate, remember the observed stratum mean is an estimate of the true stratum mean, its precision is 1 over its variance. Okay, and the variance here, if you did the algebra, it would be given by this expression here, which crucially involves the sample size. Okay, so that does play the key role here, but these other parameters do as well. So in short, the beta 0 hat, the parameter estimate, is a precision weighted average of the observed stratum means rather than a frequency weighted average or an unweighted average. And the precision weighted average is argued to be optimal here. Okay, this brings us on to the second of two technical slides here, which is we've talked about the overall global average, really, and the mean of the stratum means, but really substantively what we're interested in are the stratum specific means. And what we really want to observe is, of course, what is the stratum mean in the population at large. And remember, we denoted these beta 0j, but we only have a sample of data, okay? So what we observe is just the observed stratum means. But we critique these because where they have very small sample size, they're very erratic. So is there some kind of way that we can use the observed stratum means, to use the data that we have to make some inference about the actual quantity of interest? And the answer to that is yes, okay? And it's going to be called empirical Bayes prediction. And it's a little bit like doing a linear regression of the thing of interest, beta 0j, on the observed stratum mean. And so we're trying to predict the beta 0j's in that way. And if you work with the maths, or more likely look at the formula in a multi-level textbook, is going to be the formula that you can see here in the middle of the slide. Now, crucially, the predicted, okay, now that hat means it's a predicted stratum mean, our prediction of what we really want, is going to be a weighted average of two sources of information: the observed stratum mean, okay, and that global mean of the means. And it's a weighted average. It's not the weights aren't 0.5, 0.5, an unweighted average. Rather, it's weighted average by this term R, which is called the reliability. And not only that, but for each stratum, the weighted average can differ depending on how the reliability changes. And the reliability here is also, once again, got the sample size in there. And essentially, the bigger the sample size, the more weight we give to the actual observed stratum mean. Why? Because we've got lots of data points, so it becomes more trustworthy. But where you've only got a couple of data points, we're going to have a much lower reliability. So small r, and therefore a bigger 1 minus r, and then we get more weight put on the global average. So perhaps it's helpful just to jump back to the previous league table, okay, which had these rather tiny strata at the very top here. And the point is that our optimal prediction for example, stratum 334 is not going to be 35.3, because that's based only on 3 data points. Rather, we are going to optimally combine my 35.3 with my precision weighted mean across the entire distribution. Okay, and so the precision weighted mean is obviously going to lie in the middle of this league table, and so we're going to pull in the very erratic observed means, where they're tiny samples, to a great degree towards the average. But where we have lots of data, then our optimal prediction will actually be almost 33.7. So we've done that slide. And this is called empirical Bayes prediction. Sometimes it's called borrowing strength because we are using the data on an individual stratum, but borrowing information or strength from the distribution as a whole. Sometimes it's called partial pooling because we're using the data on the stratum, but in combination with the other data. So we're pooling data together. These are the terms which are used for it. Okay, so this plot illustrates how this works. So we've had this plot before. It's the funnel plot once again, where the grey circles are the 382 observed stratum means. But now we've added these black arrows, and the arrows point towards the middle of the distribution, and they show how these observed stratum means will be pulled in towards the overall average, and this is called shrinkage, and it comes from the equation on the previous slide, this combining information. Okay, so remember, for any given stratum, we're going to combine the observed stratum mean with the overall average of 28.1 given by this line here, and so we're going to have a weighted average of these two things, and we're going to end up in that case just here. But where you have a tiny sample size, then there's going to be being pulled down an awful lot by the fact that we put very little weight on that particular observed stratum mean because there's only going to be about one data point there. And so everything's kind of pulled into the middle. And this is a conservative approach. Basically, we're introducing a bit of bias here, but what we gain is that across repeated samples, we're going to have a lot more consistency in our result. So if another analysis was going to come along, take another sample of the data and look at the stratum means, their observed stratum means will be wildly different to ours, but their predicted stratum means will be much more similar to our predicted stratum means. So we're getting better replicability, but we're taking a bit of bias here. But the bias is a good kind of bias in the sense that it's conservative. We're going to pull in the extremes of the distribution where there's very little data, where we don't really want to make inferences about them, and we're going to let those kind of pull in, and then the ones which end up in the tops of the league tables are much more reliable because they've got more data. So in that sense, conservatism is probably a good thing here. Here is the league table revisited, because we're now going to base this league table on these optimal predicted stratum means, which are now over here. And because we, of course, sort by these rather than the observed stratum means, we've got a new ranking of my stratums, because these stratums are reorders. We've got the new ranks and the old ranks. But I think the most easy thing to see here is if you look at the sample sizes now of the top 5, these are all healthy. Remember previously, 4 out of 5 had stratum sizes of, was it 3 or less? Well, those have disappeared. They've been sucked in towards the middle of the distribution. And so if we are to look at a league table, and if we are to make consequential decisions of those strata at the tops, now there's a lot of limitations with doing that, but that's the reality of how the world works in terms of making judgments and decisions. Often a threshold has to be drawn, and if you're above it, something happens, and if you're below it, something doesn't. Then obviously this is a better approach than using the simple descriptives, observed stratum means. So that's one point. The other point here is now it makes sense to actually start to look at substantively, well, what are these top 5? And you can see I've highlighted in red kind of marginalized identities, and you can see the top 5 have multiple marginalized identities. So we've got females and black and low income appearing, and females appearing across the board actually, and they're all black, the top 5, and quite a lot of low income. But we don't have any school dropouts here, and we don't have young individuals. But remember, whether you're marginalized or privileged in terms of sex, race, education, income, and age, some of these kind of link more with BMI than others. We had that discussion earlier. And in terms of the other end of the distribution, where we have very low mean BMIs on these optimal predictions, we're seeing kind of privilege a little bit more. So we can see the white ethnic group traditionally viewed as privileged, and we see degree. Okay, we've got education degree levels, so that's privileged. High incomes, they've got all the power here, and these multiple privileged identities are appearing as we might expect with the lowest mean BMIs. One other thing to say here, which is kind of interesting, is that we're seeing the top 5 are all female, okay, and the bottom 5 are all female, okay. So that's kind of interesting here, and that's hinting at a kind of unmodeled interaction, okay, that females appear at both ends of the distributions, okay, because normally you expect females to either lie at the top, like more concentrated at the top or more concentrated at the bottom, but if there's interactions with other characteristics, then you might get this kind of appearing at both ends. Here is a caterpillar plot, because on the previous slide we talked about the optimal predictions. We stated their point estimates, but we didn't say anything about confidence intervals. And this is really important, because even though we've got these optimal predictions of borrowing strength, ultimately these strata sizes are not that big. And so if you want to look at an individual stratum and say something about it, you have to communicate the individual imprecision of them. And so in this plot, this caterpillar plot, what we have here is the predicted stratum mean on the y-axis. The stratums are ranked or ordered from the one with the lowest optimal predicted BMI to the one with the highest. This black line connects up the 382 point estimates, and the grey vertical lines are the 95% confidence intervals. Where they are wider, there's clearly fewer individuals in the stratum. Where they're tighter, there's more individuals, but in general, they're pretty wide. So any given stratum is pretty imprecisely predicted, and there's a lack of statistical separation between really many pairwise combinations, certainly pairwise combinations which are close together, which are the kind of comparisons we are typically making. So that's one set of things to say. The other thing to say is that what we're looking at here is focusing exclusively on the optimal stratum means, and the same was true on the previous slide. Here we're just looking at the optimal stratum means, but we mustn't forget that this only represents some 5% of the overall variability in individual BMI. Okay, we've got low discriminatory accuracy. So it is interesting and meaningful to compare stratum and to talk about their characteristics and identities, but this is only explaining 5% of what's really going on. And so that brings us into a more general debate about what's called the tyranny of the averages. And this is a critique of a lot of research and government policy and analysis, which just reports kind of headline statistics. What is the mean BMI of men? What is the mean BMI of women? Oh, there's a difference. But actually, within each of those subgroups, there's an overwhelming amount of individual heterogeneity, which is important to be taken into context when looking at these mean differences. And we saw this once again in that earlier plot here, trying to show you the massive overlap between different strata. And so one's got to be quite careful about making statements about a given stratum when it overlaps so massively with many other strata in terms of outcomes. And then that brings us on to kind of making consequential decisions off the back of this. So often, once you've kind of established or mapped out the degree of socio-demographic inequalities in an outcome, that information might be used to inform some kind of, for example, information campaigns, services, policies, interventions. And when you look at this kind of information, there's a desire to perhaps target the extremes, target the top 5 strata with very high BMI, mean BMI. But because of this massive overlap between distributions, the problem of that is that all the other strata also have many, many people who have high BMI and would benefit from that information campaign. And indeed, even in the top 5 strata, there's actually still lots of people who don't need the campaign because their BMIs aren't that high. It's just that the average is the highest. So that might flip you from that very targeted campaign on the top 5 strata to a universal approach where you just go, oh, let's forget strata altogether and just roll out the campaign nationally. But this isn't going to be optimal either, because there is some discriminatory accuracy. Remember, those 382 strata, they do predict 5% of the variation in individual BMI. So we do need a universal approach, but one where we nevertheless give a little bit more emphasis to those strata which show the worst outcomes. But really, more fundamental than all of this is what about the 95% of individual heterogeneity, which is unrelated to sociodemographic inequalities? What are the variables which are explaining that? And we really need to get a better handle on that. And those variables would clearly allow us to do a more optimal targeting of limited resources in such campaigns as to address BMI.